So what we'll do now this lecture is review the material for the midterm exam. Let me actually call these guys because they may not know that we start. So let me first, before we go into problems, kind of specify what material is going to be part of the midterm exam. So here's the material. There are essentially four things. Fourier series, Fourier transform, AM modulation, and this is going to be double sideband, suppressed carrier, double sideband, large carrier, and single sideband, and then angle modulation. Both FM and PM, although we haven't done much in terms of PM, so it's mostly going to be FM. The mode, so test mode, is going to be closed book, closed notes. However, you know, I'm going to allow formula sheet. Okay, because there are some formulas, and let's say I'm going to allow you to put some of these formulas on the sheet to help you instead of memorizing. What needs to be on a formula sheet? Make sure I would certainly put the Fourier transform table on a formula sheet. Maybe even some Fourier series table. I would put the Bessel functions. What else should be there? That's pretty much it. These are the, you know, feel free to add something that will make you more comfortable for the exam. Don't expect to study on the test, right? So the smaller this table is, right, that should give you a better indication how prepared you are. I mean, I know everything, just maybe some things to refresh, make me feel good. But if you start putting the whole notes there and then, you know, examples and stuff like that, that kind of tells you that you don't feel prepared for the test. The test is, as I said at the beginning today, we're not going to do it here. It's going to be in a different classroom. So monitor your FIT email account, because I'm going to email the class with the location of the test, where the test is going to be. If you don't get this email before Thursday, then email me or call me, right? So I'll let you know what the rule is. Okay. Anything? Go ahead.
The time is going to be like.
The time for this semester, we have actually beautiful luxury that we have back-to-back classes. So it's going to be 3 hours from 1 to 4. It's going to have a lot of problems, but they're going to be easier problems, right? And you know, you've taken the exams from me before, so you know I give a little bit over 100 total number of points for grabs. Everything above 90 is going to be A. So there will be some room for you to mess up something and lose some points somewhere and still have a good grade.
Okay, we can get like 2 hours and a few problems.
No, because and I'll put this on a tape, right? So it's actually good. I shouldn't be saying this, but I'll say it anyway. My niece went through high school, senior year of high school, and I closely watched how they're tested in high school. And I've learned so much from it, right? What they do in high school, they give a lot of problems. Not all of them are difficult. There are easy problems, there are not so easy problems, there are hard problems. All of them are put there. For example, they get, and I'm kind of converging to that mode. They have like a couple of hours, they have 30-something problems to solve in that couple of hours. And they're not expected to solve all of them, but actually by doing so, you're minimizing somehow luck, right? Because if I give you 3 problems, if you just don't know one particular section of what we covered, 1/3 of your grade goes away, right? You might have studied, you know, everything, but it's just your luck that you picked the area I picked the area that you didn't study. So by giving you a lot of problems, I'm actually surveying the entire thing, and I'm getting a better understanding of your overall knowledge. So that's why, you know, I'm going to try to give more problems, easier problems, but exercising different parts of the material. Right? That's the thinking here. Right? Go ahead.
The ones the exam is going to be more like questions from the practice. No?
The exam, okay. The exam is going to be made out of problems that I did in the class. So review problems done in the class. The problems assigned for homework from the main textbook, and the exercise problems assigned from the problem book. All of them are going to take a pool of problems, and I'll probably actually pick, I'll give you a secret, I'll go through these problems and pick some of them, maybe change some numbers, maybe if they're too difficult, make them easier, if they're a little easy, make them a little bit harder. But kind of, this is going to be the pool of material that I use to create. Also, since I have now, there's probably 100+ problems that I'm assigned or exercised or something. So I'll make at least 2, maybe 3 groups, right? So that, you know, I minimize the challenge to, you know, look over your shoulder or whatever. You know, you're gonna know that whatever.
We're gonna change the class.
Yeah, we're gonna change the class.
Not if you're gonna do like a different version.
This is really not being policing, just making sure that you get least amount of distractions, right? There's no distraction. It's you and a piece of paper and the problems that you're assigned, right? There's no need to, because you're just losing time trying to find stuff around. So that's how it's going to be, right?
Yeah, the reason why I asked that is because you mentioned easier problems, but I know at least on my part from the homework, some of that was pretty
hard. Yeah.
Yes.
Yeah. I agree. And then what I do is always I try to solve them. Nominally, I reject the problem if it takes more than 15 minutes. You know, if it takes me more than, let's say, 5 to 10 minutes, then I know it may take you more than 15, right? But that's not to say, okay, I don't study, so it takes me 3 hours, right? I don't know, right? You know, really it's kind of gauged by how much do you need to write, right? So I'm going to try to avoid problems with extensive integration, especially, you know, if you integrate by parts, you know, then it kind of tends to blossom and it takes a lot of space. But I'm going to try to emphasize problems where there's some sort of understanding. Like if I give you Fourier series, and I tell you this openly, if I give you Fourier series, I'm going to try to squeeze some sort of symmetry, some sort of, you know, delta pulses, some sort of things that helps you calculate. Okay?
Everything you mentioned on the board is from assignment 1 up to assignment 8, which is covered.
Is that true? I haven't. Yeah. Okay.
Yeah, is that right?
We can check, but this is the material. I forgot when we started going into this. When was the last one on FM? Here's FM. So a lecture. No, this is what is this? This is problem solving session number 2 was lecture 18. So problem solving session number 2 covers the material. So lecture 11 comes under this, right? Lecture 10 does so too, right? So 10 and 11, I guess everything that ends with the lecture 11 comes on because then lecture 12 was now review of the end process. Okay? All right, so here's what happens. I have a whole bunch of problems that I solved that I'm going to post today. We can go through these. I have some questions, so I'd rather answer your questions on the material and homeworks, and these problems are going to be posted anyway. So let's just go first through some of the questions. The first one was this problem 313, and I probably said that before. The book is full of errors. I don't know if you noticed. There are some of the problems that have, missing t greater than 0 or missing some things. So some of these questions that you're going to be asking, I actually expect, having taught this class before, there will be some problems that are missing something, right? So I expect them to come back to me as questions, right? So let's first look at this one. I don't know if this one is that, but sometimes this will happen. So we have an AM signal generating by modulating carrier. Carrier frequency is 800 kilohertz. So that's your AM radio broadcast band. Your message signal, M of t, is equal to sine 2 pi times 1000 t plus 5 cosine 2 pi times 2000 t. See here, for example, there's double t, tt. And the AM signal is created. Signal, which is u of t, is equal 100 1 plus m of t times cosine 2 pi fc t. Okay, so first one is easy. Determine the spectrum of AM signal. Do I need to determine the spectrum of this? You would have u of t as 100, 1 plus whatever is here, sine 2 pi 1000 t plus 5 cosine 2 pi times 2000 t times cosine 2 pi fct. So the spectrum of this signal will have 5 components. It will have a component on the frequency of the carrier coming from this guy. It will have 2 components coming from this sine multiplying this cosine. There will be at fc plus minus 1 kilohertz, and this one will be at fc plus minus 2 kilohertz. There will be appropriate magnitudes, half of this one, half of this one, and just this one. And then there will be phases where this sine can be seen as the cosine that's advanced by, that's delayed by pi over 2. So just the drawing this is relatively simple. When it comes to these problems, you can draw double-sided or single-sided, whichever one you prefer. Just put a note, single-sided. I'm actually happier when you draw single-sided because it's a half of a job, right? You just draw one side as opposed to 2, but either one is fine. So that's the second thing is determine the average power in the carrier and in the sidebands. So if I look at this signal, u of t, it's going to be let's say 100 cosine 2 pi fct and then it's going to be plus 50 cosine of 2 pi fc plus 1k plus some pi plus 50 cosine 2 pi fc minus 1k plus some pi, and then plus 5 times 100, so 250 cosine 2 pi fc plus 2k plus pi 1 pi 2 pi 3 plus 250 cosine 2 pi fc minus 2k plus pi 4, right? How did I write this? Well, here's your carrier, right? 100 times this 1 times this cosine. Then I have 100 sine times cosine, right? And this will give me 50, half of that 100. Cosine is plus frequencies, different frequencies, and there will be some phase adjustments coming from multiplying sine and cosine, right? And then this is 100 times 5, 500, half of that 250, and 250 here, and this is the sum of the frequencies and the difference of the frequencies. So the power of the carrier here is going to be 100 squared over 2. Right? So 100 squared over 2. Power in the sideband is going to be 2 times 50 squared over 2 plus 2 times 250 squared over 2. Okay? So that's on the carrier. And then power in the side. Follow so far? The next one is a tricky. What is the modulation index? Go ahead.
You multiply by 2 because it's 50 and 50.
50,
And
50, 250, 250. So you have the power of this one is 550 over 2, 50 squared over 2, and then 50 squared over 2, so 2 of them and then 2 of the other ones. Sorry. The part 3 is tricky. What is the modulation index? And this is where this is where it becomes a little awkward, right? What we learned in class is that U of t in a double sideband large carrier was given as some magnitude 1 plus a m n of t times cosine 2 pi f c t. This is what we learned to be a double sideband large carrier. This mn was a normalized message signal that was always said to be between 0 and 1, right? This is mn of t was defined as the m of t divided by the maximum of the absolute value. This is what we call normalized message signal. In other words, you make sure that this mn of t is always captured between -1 and 1. And then a, we always set to be between 0 and 1 as a modulation index. Here it doesn't work, but I looked at the problem. He never says that this is a double sideband large carrier. It's just some signal of similar form. So if you treat this as m of t, then what you need to find out first is what is the maximum of this one, right? And you divide by the maximum of that. And then you look at, and then 1 over that becomes your index. So here's, I don't have, actually I do. So what I would do is plot this first and determine the maximum value. I mean, you can take the derivatives and stuff, but that takes time. So let's see if I have my calculator. I don't. Anybody with a calculator? Oh, I do. So let's look at this waveform. It's going to be sine of 2. Make sure your calculator is in radians when you go on a test. That's one of the most common source of errors. So 2 times 5 times 2000 times x. And I need to plot this, say, from 1 millisecond to 1 millisecond. All right, so if you look at the maximum of this, so it's 2 somehow. Is this even possible? No, because I forgot this 5.
5.
Is it 5?
Yeah.
The 6? Is it 6? Can they be? No, because they're never in phase, right? So the magnitude is not 6. So I mean, just it is between 5 and 6. I forgot to put the 5 in front of cosine. All right, so here we go. Plot. Erase, draw. Oh. Yeah. So it's 5.84. Right, so the maximum of m of t is 5.84. So your mn of t is going to be your m of t divided by 5.84. And now I can write this signal here as u of t is equal to 100 times 1 plus 5.84 times n of t times cosine 2 pi c t. So your index here, A, is equal to 5.84. Right? Which is not very useful, right? Because index has to be between 0 and 1. So it just works out in this problem that it's high value if you apply the definitions that we have in the class. So, but this is part that you need to understand. The form that we have is this one. A, 1 plus A times the normalized signal times the index, modulation index times the K, right? This signal, the normalized signal, I'm going to obtain by taking the m of t and dividing by the maximum value of m of t. And in this case, it's 584. So message normalized signal is m of t times divided by 584. And to get back that signal, I need to put a 584 here as a modulating index. Okay. And what is the peak power delivered to the load? So, say again? No, be careful. What is the peak power? The power is equal to voltage squared divided by the resistance, right? Remember, the resistance for this signal was set to be 50 ohms, right? So the power here is a function of time. This is what we call instantaneous power, right? So to determine the peak power, you would have to square this whole thing and then find its maximum value on a 50 ohm resistor. So power of time here is going to be 100 squared divided by 50, and then 1 plus sine 2 pi 1000 t plus 5 cosine 2 pi times 2000 t quantity squared times cosine squared 2 pi c t. So that's P of t, right? And this is a function of time. The average power is what we calculate when we do this, right? This is average power, magnitude squared. To get to that, you have to take many cycles of the sinusoid on an average. But I would say here, T max is going to be something on the order 100 squared divided by 50, 1 plus 584 squared. That's the maximum power.
I think max of m of t it should be equal to 6 because you take a look only mt from the.
No, because the magnitude of this is never 6.
From mt.
Magnitude of this is never 6. Why would it be 6?
If t equal to 1 over 2000.
Okay, let's substitute. So if t is equal to 1 over 2000, right? Then m of t is going to be sine of 2 pi 1000 over 2000 plus cosine, 5 times cosine 2 pi 2000 over 2000, right?
Yeah.
Now, 1000 over 2000 is 1/2 times 2 is 1. Sine of pi is 0. So this is 0 plus cosine of 2 pi is equal to 1 plus 5 is 5. Okay? So the value is 5. That's not the point of the maximum, right? Point of the maximum is when t is equal let me just sit here. It is somewhere around 1, 2, 3, 4, 5. Only doesn't give you that. So if you set t equal to minus 0.2462 milliseconds, then you get your value to be m of t as minus 5.842. That's the maximum of this function. The extreme, it's a minimum. The reason why this is not 6 is because these two guys are out of phase, right? If this was a cosine, then they would at some points align, right? But it's not, it's sine, right? So that's the reason. So what you need to do is be careful and plot this. Once you plot this, it looks somewhat like this, right? Where there are these humps down where the maximum occurs. Okay? Any other questions? Anything from the homework? Okay. Let me then do a couple of the problems that I have. So the first problem I have is Fourier series problem. So I have a function that looks somewhat like this. It's a triangle here, triangle again. So this is my x of t. This is 0, 1, 2, 3, minus 1, and so on. So x of t is given as lambda, sum, when n goes from minus infinity to plus infinity, lambda of t minus 2n. So that's my function here that is obviously periodic. What is the period of this function? 2. Period is 2. Excellent. And the question is find the Fourier series and determine the number of components that is required so that 98% of the power is captured. So first one is find Fourier series. Now, people have different preferences. When I'm asked to find Fourier series, even to this day, I always go with the form number 1. That's the one that I can relate the most to. I personally make the least amount of errors when I'm doing that. You can choose, if nothing is said, all 3 forms are valid, but really the one that you can calculate is form 1 and form 3. Form 2 doesn't have its own calculation form. So the first, go ahead.
Excuse me, sometimes I find it difficult to find the mathematical equation.
For this?
Just for example, so for another function, it's gonna be, it's hard, to figure out.
Correct. What can I tell you?
So it's gonna be an exam.
Let me go through this and let's find out what is the difficult part. I know what you're talking about, and it's really just a skill, right, that you acquire by doing problems. But let me go and see if I can come up with some ways how you do that. If what I want you to at least understand, where is the difficulty, and if you have that difficulty in test, just ask me, and I'll just give you a hint how to do it, right? Usually I assume that, you know, from here you can just write this out, right? But if that's where you get stuck, just ask me. Go ahead.
To help us out, will you provide us the graphs so we can find like the period and stuff like that?
Graphs are, yeah, I either give you a graph or I'll give you this, right? It's equivalent, right? So,
Well, in this case, you gave us both.
in this case, I gave you this and then I wrote this one out.
Yeah.
Oh, I see.
That's the best thing, I think.
I didn't know that. Okay.
Yeah.
Yeah. This is,
Right in both.
yeah, it's either one. I mean, this is fine, right? This should be easy to see this from this and this from this. They're the same thing. But really, most of the time, somebody gives you the graph, right? Go ahead.
If we have only the graph, how do you know it's shifted to the right, not to the left? It can be, if I would write the formula, I can do it like t plus 2a.
Fine. I'm going to give the same result.
Okay.
Same result. You may actually try. Right? What he's saying is, how do I know that this is formed by taking these guys and just moving them, right? But it's the same as if you do this, right? So I could say that this is equal to sum when n goes from plus infinity to minus infinity, lambda of t minus 2n. Same thing. Or I can say this is sum when n goes from minus infinity to plus infinity, lambda of t plus 2n. All of them give you the same function. Okay, so we decided to work on a Fourier series. So the first thing I always do is I say, okay, x of t is going to be equal to a0 plus sum n goes from 1 to infinity, an cosine 2 pi n f0 t plus bn sine 2 pi n f0 t. And I know this may seem redundant, but you always kind of write this down. It helps you understand what needs to be calculated. And I always put here f0 is equal to 1 over period, which in this case is going to be 1/2. Okay? And that's where the calculation starts. And we've seen that calculation of these things has 3 parts. One is you calculate a0, calculate b, and calculate a and calculate bn. So the first thing is I calculate a0. And the first thing I want you to do is eyeball this and tell me how large is f0. A0. How large is a0? 1/2. Do you all see that? Yeah, average value is about 1/2 at least, right? So you can say it should be around 1/2.
It's a DC value also.
DC value, average value, that's all the same statement. So a0 should be 1/2. So how do I calculate a0? a0 is 1 over t, integral over t, x of t dt. I'm going to calculate this. I also notice what kind of symmetry does this function have? Even, right? So I'm going to, instead of integrating from -1 to 1, I'm going to integrate from 0 to 1 and then multiply that by 2. So it's going to be 2 times 1 over period is 2. Integral from 0 to 1. Now is where the difficulty is. What is the function in this interval, right? And really, this is kind of 1 minus t, right? How do you see that? Well, this is a straight line. What's the slope of this line?
By 2 minus
Minus 1, right? It goes 1 down per 1 horizontally. So the slope is -1. What's the offset? when t is equal to 0, where does it cross? 1, right? So if you look at this, the line, the equation of the line is AT plus B, right? That's the equation of the line. A is the slope. The slope of this line is -1, right? It goes down 1 unit per unit, right? So this is minus t, and then this B here, we call that intercept. That's the point where the line intersects with y-axis. And when t is equal to 0, B is, you can see here, if t is equal to 0, then y is equal to b. So at point t equal to 0, y is equal to 1. So that's the value for b. So that's the equation of this line. Now, sometimes it's easy as this, sometimes it's harder. You have to, if you get stuck, then ask me. So then you have dt, right? So if I integrate this, this is t minus t squared over 2, evaluated from 0 to 1. So from 0 is 0, so when I specify 1, it's 1 minus 1/2 is equal to 1/2. So I guessed it, I obtained it. Do I need to even go back to this? No. Chances of making errors to confirm your erroneous guess are very slim. So the next part is we calculate an. An is equal to 2 over t, integral over t, x of t, times cosine 2 pi and at 0 t. In our case, I'm going to use, again, symmetry. So it's 2 times 2 over 2, integral from 0 to 1, 1 minus t times cosine 2 pi and at 0 t. Okay? So this is this splits into 2 integrals. One is in 2 times integral from 0 to 1 cosine 2 pi times n times 1/2 t dt. And the other one is minus 2 times an integral from 0 to 1 t cosine 2 pi and 1/2 t dt. And I call this one I1. And I call this one I2. I1 is very easy to solve. I1, that's an integral. Integral of the sine is the cos, of the cosine is the sine. So you end up 2 times sine of pi n t over pi n, evaluated from 0 to 1. When I substitute 0, it goes to 0. When I substitute 1, I have sine of n pi. What's the sine of n pi? 0. So it's always 0, right? So that one is okay, very easy. I2 is minus 2 integral from 0 to 1 t times cosine n pi t dt. And this one we have to do by parts. So u is equal to t, du is equal to dt, dv is cosine n pi t over dt. Therefore, v is equal to sine n pi t over n phi. So I2 becomes equal to minus 2 u times v, so it's t times sine n pi t over n pi, evaluated from 0 to 1, minus integral from 0 to 1 v du, so it's going to be this times this, so it's sine n pi t over n pi dt. Right? You can see that this one goes to 0 right away, because when you substitute 0, it's 0. When you substitute 1, we have sine n pi again, so it is equal to 0. And then this is equal to this minus 2, and this minus give me 2 over n pi quantity squared cosine of n pi t evaluated from 0 to 1. So this is equal to 2 times over n pi squared. And then I can put here cosine of n pi minus 1. That's the value for a.
Excuse me, sir, could you, I haven't used integration by parts in a while, could you write down the whole formula?
Just the one quick integral of sine is minus cosine. So this is 0, 1. This is 1 minus cosine. Okay, integration by parts. Let's say you have it really starts by doing this. You remember all this. I'm going to give you this so that you remember how to derive it, right? Because I'm sure nobody forgot this one. If you take the derivative of this, then this is u prime times v plus v primes times u, right? So now, if you I can write this also du. Let me just do this. I can say, or let me just leave it this way. So, if I express now u times v prime from here, I can say u times v prime is equal to u times v everything prime minus v u prime, right? And then if I integrate both sides, you get that integral of u times v prime is equal to u times v minus integral v u prime. Right? And if I substitute this v prime with, so you get u times dv is equal to u times v minus integral v d, right? So that's the integration by parts. You start by actually this formula here for the derivative, and if you integrate u dv, then it's u times v minus v du. In this case, u, I said this to be t, dv is cosine n pi t dt. So I have here u times v minus v, which is this part, times du, which is dt. So that's my an. And then part 3, what is bn? 0. Bn is 0 for every n. We have that on account of symmetry. This function has an even symmetry. Therefore, there are no odd components that participate in building this function. So now, once I determine all of this, then the last step is you kind of write it up. It's 1 half plus sum when n goes from 1 to infinity, 2 over n pi squared times 1 minus cosine of n pi times cosine 2 pi n times 1 over 2 t. So that's the Fourier series associated with the graph over there. Now, frequently asked question is, how do I determine the number of components that I need to represent this signal? You know, remember the way we see periodic waveform when we put Fourier series glasses, we have it built out of harmonics, right? Each of these harmonics carries certain percentage of the overall signal power, right? At some point, the higher order harmonics are going to have so little of the power that it's not worth even considering, right? And we usually set a threshold. We say, well, up to what frequency do I need to go to capture certain amount of power? So to perform that analysis, we have to do first, determine the signal power directly, and then add components until we reach certain percentage of that power. So let's do that part B. This is part B. So what components do I need to keep to account for 98% of the power? Let's first determine the power of the signal directly. So, how do I determine the power of the signal? If the signal is periodic, then it is 1 over period, integral over period, magnitude of the signal squared dt. So I need to square it. Now if I square this signal, I can say this is 2 times 1 over 2, integral from 0 to 1, 1 minus t, quantity squared dt. Right? That's the square of the signal, integrated only this section here, and then multiply that by 2 and divide it by this. Now this can be done various ways. I usually do it as an integral from 0 to 1, t minus 1 squared d t minus 1, which is t minus 1 over 3 from 0 to 1. When you substitute 1, it is 0. When you substitute 0, then it is minus 1/3. So minus minus is just 1/3. Okay, so that's the power of the signal. Okay. Now let's look at power of individual components, right? And in order to do that, you just write them out. So if you look at A0, that's the first component that we have. That one has a value of 1/2, right? So I'm going to kind of write here power 0 and so on. So A1, that's the first component that I have here when I substitute n equal 1. So I have 2 over pi squared. 1 minus minus 1 is 2, right? So I have 2 times, or I should say 2 over 1 squared pi squared times 2, which is 0.4053. A2 is when I substitute 2 here, but we'll see what happens when n is equal to 2, cosine of 2 pi is 1, so it's 0, right? So the second component has the magnitude of 0. The third component is 2 times 3 squared times pi squared times 2 again. And this is 0.045450. And then the fourth component is 0. Fifth component is 0.0162, and so on. And you can see how quickly these guys go to 0, right? This component is 0.0, so it's 1%. You know, this one is 4%, this one is 40%. So this one is, 40 times smaller than this one in magnitude, 160 times smaller than it in power, right? So it really kind of nosedives really quickly. So now if you look at power-wise, if I were to keep just the first component, just say like this, first component, I would have the total power 0.25, and 0.25 divided by, let me just use a little bit over here. I know Masood is not going to like it. Because we have an agreement to just stay in this side of the board and then move to this side of the board. So, but if I look at P0 over P total, is 0.25 divided by 0.33, right, periodic, so this is 0.75. So for this waveform, 3/4 of the power is just in the DC value. See that? The power of the DC component is 1/4, power of the total component is 1/3, so 3/4 of the power is in the DC component. If I look at now and I sum these two together, then you have this power total 1 is equal to 0.25 plus 0.4053 squared over 2, right? So that's the power of the DC component plus the first harmonic. And this ends up being 0.3 3, 2, 1. So P total 1 divided by P total is going to be 0.3321 divided by 0.33, and this is 0.9964. So to capture 98% of the power of this signal, we just need the first two harmonics. Okay? So now I can say my x of t approximately is just 1/2 plus whatever is the 0.4053 cosine 2 pi times 1 over t. That's a good approximation of this signal, within a 98% of the power. So you can just model this signal as a pure cosine. And you can see that if I do this, right, this is 1/2. Here's the cosine. See? Right, so I can form this signal by taking a cosine, lifting it up by 1/2. And I'm going to capture 98% of the power of this signal. The problems are here. Right? It's going to be rounded a little bit, but these are the fine details that have a small amount of power.
Why zero component you don't divide by 2, but the first component you divide by 2?
First component I don't divide by 2.
Yes, but second, but A1 you divide by 2.
By 2. Who knows the answer to that? First component is a DC component. The second component is cosine. So the power of the DC component is the DC component squared. The average power of the cosine component is the magnitude squared divided by 2, because I'm calculating with average powers. So all other components are going to be divided by 2, not only the first one, all the other ones. Okay. Remember our Parseval's theorem that says the total power is A0 squared plus sum when n goes from 1 to infinity, an squared over 2 plus bn squared over 2. This is the contribution of each individual term. So if I have the DC component, I'm just going to square it. But all the AC components, taking both cosines and sines into account, we would have to square the magnitude and divide by 2. Go ahead.
Not for you to do it, but would you be able to get the same result if you did complex Fourier series on this?
Absolutely, you better get it. They're all equivalent, right? They're all equivalent. We can do it really quickly. You can see, you don't even have to do it. You can see quickly that it becomes A0, or actually x in a complex form, x of t is going to be sum when n goes from minus infinity to plus infinity, xn e to the j 2 pi n f0 t. Right? That's our complex form. x0 is calculated in the same way. It's 1 over t, integral over t, x of t dt. So you can see that this is exactly the same thing as a0. X0 is the same as a0. xn is calculated as 1 over t, integral over t, x of t e to the j 2 pi n f0 t dt. But watch this. In this case, I have that this is 1 over t, integral over t, x of t, cosine 2 pi n f0 t, plus j sine 2 pi n f0 t. Pi n f0 t. And this is where I'm going to use the symmetry. If x of t is even, then x of t times cosine of t is an even function, right? So I'm integrating that over symmetrical borders, I'm going to get something. But if x of t is even and sine is odd, product of even and odd is odd. So integrating odd function in symmetrical borders gives me 0. So in this case, this becomes 2 times 1 over 2 integral from 0 to 1, 1 minus t times cosine 2 pi times n 1 over 2 t dt. And if you look at this is just a half of your a0. Right? So it's the same integral that you're going to be calculating. Okay? All right. Let me do another problem. Is there a question? Okay. So problem number 2. I'm given a signal that is of this form. X of t is e to the minus alpha t when t greater than 0. So this is the guide how this function looks like. X of t. And the question is find the Fourier transform of find the Fourier transform of x of t. And then part number 2 is find the Fourier transform of x of t times cosine 2 pi fct. Now that's this is what you should expect for Fourier transforms, both to know how to find these transforms, either using table or however you find them, but also properties of the Fourier transforms. What does it mean when you delay stuff in time? What does it mean when you multiply with the cosine? What does it mean when you take the derivative? What does it mean when you integrate? Right? All of these are the properties. So here it's very easy to. Part 1 is Fourier transform of e to the minus alpha t is equal to 1 over alpha plus j over pi f. That's a table 1. It's evaluated really easy, by just straightforward integration. And then in part 2, Fourier transform of y of t. Now, which property of the Fourier transform we're going to use here? Modulation property. If I multiply it by cosine, then I'm translating the spectrum of the signal to plus fc and minus fc and scaling it down by 1/2. So instead of just doing this directly, what you're going to do is you're going to say 1/2, and then x of, let me just write x of f plus fc plus x of f minus fc. That's the Fourier transform of modulation property of the Fourier transform. So here you can just write 1/2. X of f plus fc is 1 over alpha plus j 2 pi f plus fc plus 1 over alpha plus j 2 pi f minus fc. Okay? And you can tidy this up, but I suggest don't waste time. Don't spend time on that. If you write this and this, it's okay. You don't have to put it, unless I say put it in a magnitude or phase or something specific. This is fine. This is from this, we know how to.
So we don't have to integrate it, just use the
You don't have to do anything if you can do it other ways. If you don't know how to do it otherwise, then you have to integrate.
Okay.
But if you call and if you say, okay, on the virtue of modulation property of the Fourier transform, I know that this is it, that's fine. Because we've done this many, many times so far, right?
Y of t is the exponential times the cosine.
It's x of t times cosine. Oh, I didn't write it. So this is Fourier transform of y of t. Y of t is this guy, x of t times cosine.
Okay, and you use the table for that?
For this one?
For number 2?
No, I'm using a modulation property of the Fourier transform. Remember we said this is the problem. If x of t has a Fourier transform x of f, then x of t multiplying cosine 2 pi fct has a Fourier transform 1/2 x of f plus fc plus x of f minus fc. That's the one of the properties that we demonstrated in class, and we used it extensively, remember, because this is our double sideband suppressed carrier. If I instead of x I put m, then I have double sideband suppressed carrier modulation signal. And we saw that the effect of multiplying your message signal with the cosine is essentially translation of the spectrum of the message signal to the carrier frequency. Right? So that's one of the things that we use quite a bit. Okay, let me go through one more real quick. This is AM modulation. So it says consider a circuit given in this figure. So you have M of t plus cosine of 2 pi t and squared, and then here you have bandpass filter that picks the proper piece. This is what I'm going to call x of t, this is going to go y of t, and this is u of t. And it says, show that this can be used as a AM modulator, and then sketch the amplitude spectrum of x of f, y of f, and u of f in a frequency domain. So how do we do this? Well, first, let's show that this is an AM modulator. So the way how you approach these problems, I talked about it last time, these are just about the simplest problems. I mean, they look a lot of times complicated, but all you gotta do is kind of say, okay, forget about big picture, let's do one step at a time. And one step at a time, you travel through this block diagram, evaluate signals as you move along. So really, x of t, the simple step is what? M of t plus cosine 2 pi fc t. Then your y of t is whatever is x of t squared, right? So you take m of t plus cosine 2 pi fct quantity squared. So this is m squared of t plus 2 m of t times cosine 2 pi fct, and then plus cosine squared 2 pi fct. Right, just square first square plus 2 times first times second plus the second square. Now, y of t can be written as m squared of t plus 2 m of t times cosine of 2 pi fct plus 1/2 cosine of 2 pi times 2 fct. Where is this coming from? Cosine squared is 1/2 plus 1/2 of the cosine of twice the frequency. So that's y of t. Now, which part out of these is your double sideband AM? Which one? This one, right? So this is the part that we care about. So this is double sideband suppressed carrier. Okay? So if this is to work, this u of t is going to be essentially 2 m of t times cosine 2 pi fct, which is indeed AM modulated.
Okay. What is the last box on the
This one? Bandpass filter.
Bandpass.
Just traditional symbols, right? This thing is a low pass. Right? This thing is a band pass. What is this one? High pass. So these are you know, if you look at radio schematics, this is what is always there. Go ahead.
Let's see, why is the rest of it getting filtered out?
Well, that was my next. So let's figure out first where are the spectra of all of these individual signals. Right? That's really the key thing here. So let me first start by M of f. M of f is going to extend from -w to w, right? This is my signal, message signal that I use for modulation. Now, how does x of f look like? X of f is an addition between two signals. Your M of f, which goes from -w to w, so this is M of f. And then you have your carrier frequency, right, which is at the frequency fc. Okay, so this is x of f, the magnitude spectrum of x of f. Now, how about the spectrum of y of f? That's the key guy, right? So let me sketch y of f. Let's first start with the components that we are quite familiar with. Where is this component? The delta pulse at the origin, right? So there is a delta pulse here at the origin, 1/2 delta of f that belongs to this one. How about this guy? That's half of whatever at 2fc. So it's very hot out in the frequency domain. Let me call this -2fc. And here it's 1/4 delta of f plus fc. And then here 2fc. It's 1/4 delta of f minus fc. So we took care of this guy. We took care of this guy. How about this one?
Square over.
Huh?
Yeah, it's quarter. No.
2W?
And minus 2FC.
Quarter, right?
Yeah.
fc minus fc, and this is fc. So there is this guy. This is m of f plus fc, and this is m of f minus fc. So that takes care of this one. So the only problem child left is this one. Where is the spectrum of that guy? 0. Around the origin, right? So it's a. But what also we know about it? How far does it extend? It's 2w. How did you determine that?
Double confusion.
Beautiful, yeah. Because here's what he's saying. M of t in a time domain squared is m of t times m of t, right? So m squared of t can be seen as the multiplication in the time domain of two signals. One is m of t, and the other one is m of t too, right? So multiplication in a time domain is convolution in a frequency domain. If you have two signals that, if the signal m of f has a footprint from 0 to f, then when you convolve it with itself, it will have footprint from 0 to 2f. So in other words, here I have, not f, 2w, sorry. Minus 2w to minus 2w, and this is your Fourier transform of m squared. The shape of it is not that important. What is important is the footprint of the signal. And if the signal occupies from 0 to w, then its square will occupy from 0 to 2w. Right? That's the way how you can see it, one way how we can understand
I
it.
don't see that. How did you grab the second component, which is 2m of t cosine?
This one?
Yes, it's 2.
This is the same thing that I have here, right? Because I have m of t multiplying cosine, right? So this is 1/2 m of f plus fc, m of f minus fc. Because I have 2 m of t, this 1/2 goes away, right?
Oh, so, okay.
Right? So what this does, it translates M here and M here, right? So now it becomes, we go back to Jason's question and said, well, how did I know that this is the output signal? Well, the purpose of this circuit is to do AM modulation. So it needs to pick out of all of these components that are being generated, the ones that is an AM modulated signal. So which one will it pick? This one, right? So it will actually, this bandpass filter would be like this, right? Right? It will reject this mess here around the origin. It will reject the double frequency component and pick just the component around the particular frequency.
Shams favors low pass. I don't know if you know this. It doesn't do a lot of.
Because Shams looks at demodulation.
Okay.
I'm looking the other way around, right?
Okay.
When you go from the frequency of the carrier to the baseband, then you have to use low pass because everything else is extra, right? You don't need everything else. When you go from the baseband to modulated carrier, then you have to pick the part that's around the carrier, right?
Okay.
Reject. So depending if you're doing modulation or demodulation. If you look at the transmitter side of all the communication equipment, the last stage is a filter that is a bandpass filter that rejects out-of-band emission, right? That filter lets your signal go through and then rejects everything that you're not supposed to be transmitting. Because otherwise, if I transmit here, I'm going to be stepping on somebody else who's authorized to work in this range, right?
Mm-hmm.
So when you go towards the higher frequency, you always have last filter is your bandpass filter. When you come into the receiver, the first filter is bandpass filter to reject everything that is not your signal, but the last filter is going to be low pass because a lot of times, actually all the time, you're demodulating all the way to the baseband, and then you got to reject everything that is above the frequency of your signal.
From my understanding, the low pass filters out the lower part of it, the high pass filters out the high part, and the band pass filters out both parts.
No,
Is that right?
Yeah, it is. The bandpass can be seen as two of them working in I guess together. Here's the low pass, right? Letting the frequencies from 0 to W go through. And then here is a bandpass, letting frequencies above some, let's say, F low, above that frequency go up. So if you look at, if I filter with the solid one and with the dot one, the part that will go through is this part.
Right. But when you look at these, the pulses, you in previous lectures, you called like the I think it was the left side, the upper band, and the right side, the lower band.
Lower sideband and upper sideband?
Exactly.
Yeah.
And to me, I would, like if there's lower band, you basically draw a line down the middle of the triangle and remove the lower band and you keep the upper band.
That's a single sideband modulation, and
Right.
we did that, right?
Right, and in this, wouldn't you just remove the triangle since it's filtering out both the upper and the lower?
No, because I want to generate double sideband suppressed carrier, right? So double sideband suppressed carrier is this. So I want this to go through. I want the whole thing to go through. I don't want to.
So it's more of a selector than a filter?
It's a selector.
Okay.
That's what it is.
Okay.
It's a selector, right? It selects. I mean, what is a selector? It's a filter. You filter out these parts, everything.
Do we have to bring the formula for double sideband or something?
Bring, I'm not going to restrict you, right? I say formula sheet, bring whatever you need to bring. Right? You know, if you feel like you need these formulas, put them. It's okay. But you know, if you bring the whole notebook.
which one do you favor personally, the most out of these three filters?
And the one that's gonna be
You
the
cannot
example.
really favor them.
Well,
They're
Shams
all-
favors
No,
low pass.
no, he doesn't. I mean, because most of the problems that you're looking at, demodulation problems. So when you demodulate, this is what you need. And that you get out of everything by low pass, right? Because you're signaling from 0 to W, and you're gonna have all of these other components that you're trying to get rid of. So the specific use of the low pass is in demodulation as the last filtering stage. Now, specific use of the band pass is on the transmission side as an out-of-band emission rejection filter that gets rid of all of these extraneous components that you should not be transmitting. So that's when you transmit. And on the reception side, the purpose of the band pass is to reject the noise that is outside of the band of your signal. So in every communication system, you're going to have both. You're going to actually have multiple filtering stages. Most of them are going to be bandpass stages. Right? If you look at typical, for example, radio receiver, it is what we call super heterodyne receiver. It will have at least 2 bandpass filters and a low-pass filter on the receive side. First is what we call front-end filter that sits right after the antenna that rejects all the noise except and lets only your signal go through. And then the next one is going to be IF filter that is at the demodulation stage. And then once you do the demodulation, then the third filter is going to be a low-pass filter that gets rid of the product of the demodulation. So you're going to have all sorts of them, and that's a minimum 3. But depending how you do the modulation and modulation, you're going to have a lot more. Okay. All right. Well, we have a lot of problems. Get prepared. I'll send you an email where the actual answers are.